is Anthony, and today's video is on real gases.
Yeah! So hello everyone, today we'll talk about real or non-ideal gases. Please try to remember our original ideas about gases. Those ideas were these, and they're the ideas about the ideal gases. Perhaps you remember we said that an ideal gas would have perfectly elastic collisions, that the particles would act alone as single particles and never as groups, that the volume of the sample would be really the volume of the space between the particles. In other words, the particles themselves would have an almost zero volume or negligible volume in the overall space. Because the particles themselves, the volume of them would be really very tiny, so small we could ignore it. So these are the conditions for an ideal gas. Now let's talk about a real gas for a second. It's actually out in the real world. Perhaps they might be able to have inelastic collisions. Some collisions could be somewhat sticky. Perhaps the particles could stick together and act as a group or as groups. Also, the particles themselves perhaps have volume that's not entirely negligible in the overall sample volume. In other words, they would have a small volume that might not be zero. So it seems like we may need to adjust our ideal gas law to handle these non-ideal cases. So let's have a look at the conditions where the ideal gas law might make sense and where we might have to handle these adjustments. So on the left-hand side here, we have the elastic collisions, which seems like they would come from high-speed particles, which seems like they would come from high temperatures. So high temperature looks like it would be good for this ideal gas law. Also, small or zero particle volume. That means that the sample volume itself should be large comparatively, and that the pressure should be low. So when we see high temperature and low pressure, we're usually looking at a scenario where we're seeing probably something that our ideal gas law could be very useful for. It's a very gas-like conditions. While on the other hand, these real gases or non-ideal gases would have sticky collisions, which would happen at low speed, and that would be particles moving at low temperature, and large non-zero particle volumes. In other words, we would have small sample volumes, and consequently this would be at high pressure. So that this idea that a low temperature and high pressure scenario, which looks a little bit more like a liquid condition, low temperature, high pressure looks more like liquid conditions, wouldn't work so well for our ideal gases. Let's talk about particles. Ideal gas particles should be, as we said, small in volume and have no mutual attraction for one another. The real gases should be large in volume, the particles, and have strong mutual attractions. So we have to be aware of these limitations when we're using the ideal gas law. And real scenarios might require us to adjust the ideal gas law to handle the particle volumes and so forth as we've just discussed. So let's have a look at real scenarios and the adjustments that they may need. Fortunately, a famous Dutch physicist, Johannes van der Waals, can come and help us here. And this is work that he actually got the Nobel Prize for in 1910. He made an adjusted version of the ideal gas law, which we now call the van der Waals equation of state. So he took the ideal gas law that we know, our good friend PV equal nRT, and he made an adjustment. He adjusted the pressure with this n squared A over V squared term, and the volume with this NB term. The pressure term and the volume term here, A would adjust for the attractive force between particles, the stickiness of their collisions, and B would adjust for the volume of 1 mole of particles, reducing the free volume by the volume of the particles. So these A and B values would be experimentally determined for each gas, and in fact they have been done, and this is a useful way to handle gases that are not behaving in an ideal way. So in summary, here we have on the left ideal gases, and on the right the non-ideal gases. So high temperature, low pressure, small particles, no mutual attraction, PV equal nRT. That would be an ideal case. The non-ideal case is low temperature, high pressure, the opposite, large particles, and particles that would have strong mutual attraction with one another. So on the left we have PV equal nRT, and on the right we have the van der Waals equation of state with these A and B adjustments to the pressure and the volume respectively. So thanks everyone, that's a quick version, but see you soon. Do be sure to have a look at the next 2 videos in our playlist for more, and stay tuned for the next video, the introduction to our new unit, Introduction to Solutions.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.